The area of a kite or a rhombus, what is it for? We can choose the common example for kite flying in the air, or designs on balls, picture frames, or even a ceiling rose as more complex structures. By the way, a rhombus is a special kind of kite because it has 4 equal sides. Like these examples, most kites are convex shapes, but others are non-convex, commonly called darts, like the boomerang on that coffee table. And there are many more examples. Now let's consider a star-shaped ceiling rose for our situation. The figure consists of an orange-colored section and another one in blue. The measures of the 3 radii R1, R2 and R3 are given. Now let's look at a few questions. First question, what is the area of the orange part of this pattern? The second question, what about the blue one? And the last question, what about the whole design?
For the first question of this problem, we focus on the orange part of the figure, the orange star. Then we need the radii R1 and R3. This star can be decomposed into 6 identical kites as shown here. In fact, 2 adjacent sides like these are equal, since they correspond to the radii of the smaller circle, and by symmetry, that is with this axis of symmetry, the other 2 adjacent sides are equal as well. Let's draw the diagonal of one kite and repeat that for the others. Inside the smaller circle, we notice a regular hexagon. That means it has 6 equal sides. And here is something important. A regular hexagon is made of 6 equilateral triangles. So this diagonal right here is exactly equal to the radius of the smaller circle. Once we find the area of one kite, we just multiply by 6 to get the area of the whole orange star. Here we can see one diagonal in red and the other in green. The green one equals radius R1 from the smaller circle, and the red one equals radius R3 from the larger circle. Now let's use a simulation to see how we can find the area of a kite. Let's draw the diagonals D1 and D2. D1 is the axis of symmetry of the kite. Now, if we duplicate the lower triangle like this, we can see a rectangle appear above the axis, and it has exactly the same area as the kite. Remember, the area of a rectangle is length times width. So here that's D1 multiplied by half of D2. There's another way to find the formula for the area of a kite. Let's look at the triangle below the axis of symmetry. Using the simulation, we can move and flip it over to place it above, like this. By doing so, a parallelogram is formed above the axis of symmetry, and it has the same area as the kite. Remember, the area of a parallelogram is base times height, so here again we get D1 multiplied by half of D2. Let's go back to the orange star. One of its branches is shaped like a kite. Here the diagonal D1 is in red and the diagonal D2 is in green. We've already learned that the area of a kite is D1 times D2 divided by 2. In our case, that becomes R3 times R1 divided by 2. Since R1 is 30 centimeters and R3 is 70 centimeters, we get 70 times 30 divided by 2 equals 1050 square centimeters. And because the star has 6 identical branches, the total area is equal to 6 times 1050, which gives 6300 square centimeters, or 0.63 square meters. Now for the second question, let's focus on the blue pattern made of 6 identical dots. Let's take just one. It has an axis of symmetry here. That's why it has 2 pairs of adjacent equal sides, one pair here and the other here. This is still a kite, but a non-convex one, also called concave. Why? Because if you pick 2 points inside the shape and draw a segment between them, the segment might go outside the figure. Another way to see it is that this angle here is greater than 180 degrees. It's non-convex. Now let's represent the diagonals of one of these dots, D1 in red and D2 in green. Then we draw the 2 radii R3 of the larger circle. We can see that the diagonal D2 has the same length as R3. In fact, the green triangle shown here can be repeated 6 times to form a regular hexagon inscribed in the circle. That's why this triangle is equilateral. Then we see that D1 is equal to the difference between the radii R2 and R1. If we can determine the area of one dot, then by multiplying it by 6, we obtain the area of the entire blue pattern. Now let's run a simulation to see how we can easily find the area of a dot, a non-convex or concave kite. When we move this point, we generate different dots, always keeping D1 in red and D2 in green. Starting from the axis of symmetry, we can take the lower triangle, flip it over and move it up like this. Once it's placed above the axis, it creates a parallelogram with exactly the same area as the dot. And in the end, we get the very same formula as for the convex kite, the product of the 2 diagonals divided by 2. In our case, D2 is 70 centimeters and D1 comes from R2 minus R1 equals 45 minus 30, so it's 15 centimeters. The area of one dot is D1 times D2 all over 2. Plugging in the numbers, that gives 15 times 70 all over 2 equals 525 square centimeters. And since there are 6 dots, the total area of the blue pattern is 6 times 525 equals 3150 square centimeters, or 0.315 square meters. For the third question, we now need the areas of both the orange and the blue patterns. So the total area of the entire design is simply the sum of these 2 parts. Here that gives 0.63 plus 0.315 equals 0.945 square meters. There's another way to find the total area of the whole pattern. Here we focus on the purple kite and take 6 of them to build the star. Its diagonals are shown, D1 in red and D2 in green. Notice that D1 matches R3, the radius of the larger circle. which is 70 centimeters. And D2 matches R2. The radius of the middle circle equal to 45 centimeters. Using the formula for the area of a kite, D1 times D2 divided by 2, we get 70 times 45 divided by 2 equals 1575 square centimeters. Multiply this by 6 and the total area becomes 9450 square centimeters or 0.945 square meters. Exactly the same result as before. To sum up, the area of a kite, or in the specific case of a rhombus, as shown in the left figure here, is equal to half the product of its diagonals D1 and D2. Whether the kite is convex or non-convex, as shown in the right figure here, its area is given by exactly the same formula.